So, first Pear Deck question, what is the most important thing that you remember from last week? We talked about how we quantify the Earth, from spheroids to ellipsoids, how we represent those in datums, what in the world is a geoid, why is it so bumpy, what's the difference between a spherical and a Cartesian coordinate system, and what is going to happen with all of this stuff that we've learned in 2022. It's already 2020, I can't believe that. All right, I'm seeing some good answers about projections. All of this gets at how we project all of this spatial data in a realm that we can present either in a map or on a screen. It'll probably all change again someday when we're trying to do things in 3D. But for now, there's a lot of theory and science and math and fuzzing the numbers a little bit here and there to get roundish things that are bumpy onto flat pieces of paper. So we talked about the geoid model of the Earth, which is a representation of mean sea level around the globe, which is a spheroid, and specifically it is a squashed ellipsoid. We talked about datums that are in use right now in our country. We pretty much primarily use the NAD83 datum for a lot of different projection systems. And in 2022, we're going to see NAD83 go away for good and be replaced by a new model of the world for a couple of reasons. So we'll get into that a little bit at the end. And the coordinate systems that we generally use to represent all of this information are spherical systems like latitude and longitude, or Cartesian systems that we use in planar systems like an X and a Y axis. So that's the number that you end up seeing on a point on a map, and it all comes from all of this theory behind it. So right now we have the question of how do I convert data from one system to another? Well, if everything is on the same geoid model and the same datum, then it's fairly straightforward. There's a mathematical conversion from one projection to the other projection. Sometimes that's a little bit more complicated with really interesting shapes of projections, but the underlying model is the same. If we have a system where we're working with two different geoids, two different datums, and we're trying to take projected coordinates from one of those to the other, we have actually 3 transformations that have to happen. So you can imagine that's a lot more error prone. So there's not really a takeaway practice for you guys here because you don't have control over the way that you receive a lot of the data. But you need to understand what's happened to that data before it's gotten to you, and what the consequences are of converting that information on the fly in ArcGIS. You can't see it, you never pay any attention to it. It probably doesn't mean a whole lot to you, but you'll start to see weird effects of the consequences of these selections of projection systems and geoid models. So you just need to basically understand that that's all happening somewhere. And sometimes you control that happening by, say, exporting or converting one file to another projection system or another datum. And sometimes it just happens on the fly in the background in ArcGIS, and it comes out looking really bad. So a map projection is just, in simple terms, how we take that geoid model, that datum, and represent it on a flat piece of paper. So there's no way to do that without causing distortion, but there's a lot of different ways to distort the data to make it happen. So we're going to go through those today. So there's different shapes of projections that we use, and we'll talk about those. There's different distortion results that happen as a result of the selection of the projection shape, but also the type of distortion model that is used. And then there's also an effect from where you're perceiving that map from. If we're talking about a planar projection, you can perceive it from the center of the Earth, from a point on the opposite side of the Earth, or from some point out in space where you are an alien in a far-off galaxy viewing the Earth. What does that Earth look like to you if you represented it on a flat piece of paper? So there's trade-offs for each of those. These are just a couple of resources for you, and I'm gonna pull up the second one. This first one is a gallery of map projections specifically put out by Esri. Esri doesn't control projections per se, but they have definitely a fair amount of influence because they're kind of the mechanism through which a lot of the people on the planet interact with projections. So they have a lot of good resources there. And I think I also linked some of their reading materials later on. But this gallery I think is helpful. I also heavily drew on the imagery in Wikipedia. There have been a couple of people that have developed a lot of really consistent representation of different projection models that makes it easy to visualize what's happening there. You know, some of these are really strange, and you're very seldom going to be working with an entire map that looks like this, but you might be working with one little chunk of that map. So you can understand how the world around your little chunk is being distorted, or even the edges of your little chunk of that map. So I think this is a really helpful resource for visualizing, especially some of the weirder systems, which we're not going to really talk about a whole lot today, but they're fun, especially this Waterman butterfly. There's a lot of interesting stuff that goes on out there in GIS science or survey geomatics. So we start off with a developable surface and we project onto that surface. So the most common shapes are cylinders, cones, and planes. And we're going to start off talking about cylinders because historically that were some of the earliest methods used to project the Earth onto a piece of paper. So the developable surface is the geometric shape. Once you cut it apart and flatten it out, what does that look like? So we'll start off, oh, okay. That process, obviously, neither one of those is a sphere. So that process is going to result in distortion, and that distortion varies depending on the type of developable surface that you have selected, and also the area on which you try to apply it. So as you saw in some of those really funky world maps, the distortion is going to be more extreme the further you try to apply it. And then this is that point that I tried to explain without pictures, which isn't very helpful, of where you're viewing your projection from. And another point that I think is helpful on this slide is that your distortion can also vary as a result of your local ellipsoid. So if you're in an area where there is a lot of variation in that local ellipsoid, for example, Cook Inlet is an area that has its own ellipsoidal model because there's a lot of really strange stuff happening in Cook Inlet. Some of it to do with tidal issues, but some of it also probably to do with other gravitational effects. So you can have a lot larger level of distortion in your model as a result of some sort of bizarre local anomaly. One of the things that we do in conjunction with selecting the shape of projection is selecting the type of distortion that is used, applied. So distortion is essentially taking the problem of you can't represent a sphere on a flat surface and applying that problem in a predictable way, essentially, right? We know it's distorted. We've controlled how we distort it, so we can understand the effects of that selection. So an equidistant distortion holds the distance between any 2 points consistent, but you'll have distortion then in your shapes and angles or areas. A conformal projection will hold your angles and shapes consistent, so things look familiar, but they're not necessarily the correct size or the distance from each other. And then the final most common is the equal area, and that's really useful in data analysis, especially when you're trying to associate things with continents or countries or states, is to use an equal area projection. But then you have distortion in the way things look and the spacing between them. Another thing to keep in mind is a lot of these projection systems are designed for continental land masses, and don't really take into account a lot of things happening in the ocean. So if you're trying to represent things in the ocean, it's something to keep in mind is understanding where your system is centralized, right? If it's centered around the middle of the United States, it's maybe not useful for mapping the Mediterranean Ocean. C, I think it's a C, sorry. So anyway, those are the 3 most common types of distortion that are used. There's also azimuthal distortion, which keeps the direction between any 2 points. And that was really important for sailors because you didn't necessarily have a lot of control in early navigation over how fast you were going, but you could control the direction, and eventually if you continue in that direction and you have everything mapped correctly, you will arrive at your destination. So distances were maybe less important. Sizes of continents were obviously less well known, but the bearing at which you approach them was highly critical. And then the couple of special application systems that I think are relevant, especially in the Arctic. The stereographic system works well for objects in the Arctic, and then the gnomic system is used, I think, a little bit more in world navigation now because it keeps those Great Circle routes consistent. So all of that right now is just words. So we're gonna, thank you, Jean, I appreciate that. I'm definitely working on that. I don't think I'm gonna succeed today because this is a dense subject. So Jean has reminded me how many times I say on a recording, which hopefully isn't as noticeable until you go back and listen to my recordings, and then you can't get rid of it. All right, I will try to work on that. Thank you. So here's an example of distortion between just 4 different representations of Greenland. There's A, which is the global perspective. Even that is going to be slightly distorted because, as we discussed, the world is not a sphere or even a spheroid. It's a oblate ellipsoid. So somebody sat on a basketball. The item B is what happens if you take latitude and longitude and you pretend that they're square systems. They're obviously not, and you end up with a huge amount of distortion as you approach the poles because the space within the longitude is quite a bit narrower there than towards the base of the continent. Actually, I'm not sure. Probably Greenland doesn't qualify as a continent, maybe a subcontinent. Number C is the Mercator projection, which is one of the more classic and recognizable systems, but also has huge amounts of distortion towards the poles. So it was used pretty heavily in navigation between Europe and North America, and in the near equator areas of the world, but starts to really distort things like Canada and Alaska and Africa. So there's a lot of negative feelings towards Mercator because it does tend to accurately represent those low latitude, should we say, economically advanced countries, and less accurately represent the countries closer to the poles, which tend to be less economically advanced. I'm not sure if I have my adjectives all in the right place there, but you get what I'm trying to say. Mercator is falling out of favor, but still really common because it's just so classic. And it's used in the Universal Transverse Mercator system, which does some things to help compensate for some of those flaws, but is very recognizable. And so D represents a transverse Mercator projection, which we'll get into the details behind that a little bit, but it helps deal with some of that distortion towards the poles. All right, so the second piece that you select, or the third, I'm actually not sure what would be the best order in which to approach these, but something to keep in mind is your projection aspect. And the projection aspect, it just means the orientation of your projection shape. So in this case, I'm showing the cylinder to the globe. So the orientation to the polar axis between the North and the South poles on a normal system. The axis of the cylinder is aligned with the axis of the poles. So they would rotate together. For a transverse system, the axes of the cylinder versus the axis of the Earth are at right angles to each other. And this has the effect of reducing some of that polar distortion that we were talking about. And this is a kind of a visual representation of what would happen to all of those globes if it was exactly at this orientation. And then you have the oblique system, which is basically, I'm just going to randomly rotate that globe around until I get the picture that I want. That's a rather simplistic way to look at it, but there's not any specific angle or specific orientation implied by the oblique system. It just means that you've altered that angle to optimize some specific location. So those tend to be really popular for specific regional representations. So this is ignoring the question of distortion, but just showing how many combinations you can get if you just take aspect and projection into account. So you can make lots of different shapes, lots of different kinds of maps. But then you can also control the distortion. So we'll get into some of those details coming up. So I told you before, the three most common types of distortion are equidistant, conformal, and equal area. And these are just some examples of that. So the equidistant equirectangular projection is one of the earliest and most common representations. It's not the crazy Mercator system that stretches things towards the poles, but everything kind of looks weird and flat. And although it preserves distances, it doesn't preserve shape or bearing between 2 points. The conformal projection, this is just an interesting one that I selected that did some really strange things to Europe. This is not one that you would use heavily for European areas, but probably would be really great for equatorial and Southwest Asia or Southeast Asia. And that would preserve shape and angles of small areas. Obviously, it did not preserve the shape of Europe, but it's probably going to do a much better job of preserving things along its central meridian, which is the equator there. And then equal area projections, the Wagner's 7 world map is kind of a classic representation. This shows the correct areas. So it's a good thing to use for size representation, but shapes are odd and not accurately representing the shapes that you would see on the globe. But I think at this point, our concepts of the shapes of different parts of the world are so formed by the maps that we've seen throughout our lives that it would be hard to say which one of these is the most distorted unless you understood the system being used underneath. So that's something that tends to be ignored by cartographers, or they choose the one that is most familiar to them and therefore looks good to them. All right. It's a little too early to take a break, so we'll go through, I think, the cylindrical projections and see how we're doing for time. So the first one we're going to talk about is the cylindrical projection, because historically this is a system that has been used very heavily. So for a cylindrical projection, you choose the central meridian, which is the longitude to which you rotate the globe. So this is assuming that we're using a normal aspect. So the axis of the poles is aligned with the axis of the cylinder, and we're just rotating that globe around until we see the piece of the world that we want to see. There's a subset of this, which is the secant projection, and basically you're no longer enclosing the globe with that cylinder. The globe is going to stick out a little bit, and you can lessen some of the distortion between those two parallels by using that system, but you're still going to have distortion then at that equator. So the two pieces that you need to pieces of information that you need to collect is the meridian at which you're facing. So that's the, whether it's the Greenwich meridian or you've rotated around, so you have the United States or Alaska centered, and then the parallel, which can either be a single standard parallel or, in the case of the secant, two standard parallels. So this is the one that we mentioned earlier, the equirectangular projection. The latitude and longitude grid is uniform, which means that we've substantially distorted towards the poles because they're not uniform. So it's not going to be conformal, which means you can no longer use the bearings, but the distance along your grid lines is going to be consistent. So this would not be a navigational map. It would not be a map that you would probably use to show statistics around the globe, but it fully represents the globe without largely distorting, except for really close to the poles. Obviously, Antarctica couldn't possibly be that big. So this one was a cylindrical system with a normal axis. The standard Mercator projection is also a cylindrical system with a normal axis, but instead of holding the latitude and longitude as a grid, there is distortion towards the poles. So this is then becomes a conformal system and is one of the ones that I mentioned that's heavily used for navigation, because now your bearings to different points are held correct, but your shapes and your areas are not. You still have the right angle intersection of latitude and longitude, which is helpful when you're trying to grid latitude and longitude, but you have a lot of distortion of shapes and sizes as you move away from the equator. So I just wanted to throw this in here. Translating the central meridian sounds like a really fancy thing to do, but it's really just spinning the globe. You see a lot of world maps that look like the left side here, and as different powers move into more prominence in the world, you start seeing more maps that look like the right. Both of them are accurate representations of our globe, obviously, so it's, I think, a good representation of the stereotyping of the world that happens through map visualization. There are also maps produced by Korea, which I didn't include in here, that make Korea look like the majority of the globe. It's a really interesting psychological experiment. So I mentioned earlier that Mercator is politically not a very popular system. It's also not popular for the reason that it significantly distorts the size of spaces. So Canada is one of the hardest areas in the world to map because it approaches the pole, and we've chosen this pole-centric latitude and longitude system. Obviously, if we change that, if we ignore the way the planet rotates and ignore that oblate spherical model, some of this distortion would go away. But since we use those pretty heavily, there's a significant amount of distortion, and I can only watch the slide for so long, so we'll move on. But for spatial analysis, the Mercator system is not good. So then we move to the transverse Mercator system, and it has a lot of the same issues of the Mercator system. It's still a cylindrical system, but instead of being a normal cylindrical system, it's transverse. So the axes are perpendicular to each other. The axis of rotation of the globe is perpendicular to the cylindrical axis of this representative planar surface that we've wrapped around the globe. And what that does is move the distortion. So instead of having significant distortion in Canada, we're now seeing huge amounts of distortion in Africa and South America. So like we said at the beginning, you can never get away from distortion. You just have to move it somewhere else. I think this is an interesting representation of Southeast Asia too, even though they're tucked away up there in the corner. And then the ellipsoidal transverse Mercator is just a reminder that our Earth is an ellipsoid. So if you take that into account, you can better model the world, essentially. And then finally, the oblique Mercator system. I mentioned that oblique just means that you've rotated that globe within the cylinder to maximize or to optimize the mapping for whichever system you cared about. So now all of a sudden we're seeing a fairly representative size for Antarctica, which we don't have in a lot of other systems. But clearly Russia and South America are going to dominate the world. So again, if you use these systems in a small, limited application, they can be very accurate in those areas. But if you try to apply the same mapping system somewhere else in the globe that it's not designed for, it wouldn't work effectively. Another popular cylindrical system is the Lambert cylindrical equal area projection. This obviously has significant distortion towards the poles, and it doesn't optimize shape or bearing well, but it does apply a fairly consistent area. So each one of these continents, if looked at for its actual area, would be relatively accurate, especially as we've now sort of centralized Africa, which in the Mercator system, we centralize things around Europe and North America. And so Africa appeared distorted in size, but it's actually quite large. So I've included these throughout the lecture. They're a really helpful method of demonstrating the distortion, right? None of us have a really clear idea of what the actual accurate representation of any given continent is, because we've spent so much of our lives looking at maps which are distorted. So, but we understand spheres pretty darn well. So this helps to show that distortion and is a really useful system for that. So these are all taken from Wikipedia. There's not a huge amount of consistency in the way that Wikipedia describes and represents projection systems. So I don't think it's the greatest resource for that reason, but for visualizing the different reference systems, it's really helpful. So I've included those in here. And you can get at them, again, through that link that I included earlier in the lab.